we've worked our way up from one categorical variable to one quantitative variable, and then we made it harder by adding another variable. So we started with two categorical variables, and then we, in chapter 6, did a categorical variable and a quantitative variable. So for the last chapter in this class, we're going to look at what happens when we have two quantitative variables. We're going to start out by talking about correlation, and then we're going to talk about regression. So let's start out with chapter 10.1. As with the other chapters that we've done, we're going to start out talking about how to best graphically display this data and gentle introduction to some basic concepts. And then we'll, in later sections, delve into the actual statistics and quantitative work. Right. So, the data set we're going to be working with in this chapter is one that I found online that seemed kind of interesting. Back at the beginning of the discipline of statistics, there were a whole bunch of guys who were very interested in the natural world, so they set out to quantify traits of plants, and they conducted really extensive studies of human anatomy and variations in human anatomy, and through that developed some of the first principles of genetics and inheritance. One of these studies looked at people brought into the Middlesex Hospital morgue in, I think, London, for autopsy, and examined the relationship between the head size, so the box with the smallest volume that you could fit a head in, and the weight of the brain in grams. So they say they examined everyone who was brought in who didn't have some obvious brain pathology. So basically, if the brain didn't have like a massive tumor growing out of it, they were good to go. Alright, and you can see the measurements that they took. So basically, they took the length, the width, and the depth of the head and used that to compute the rectangular volume of the head for head size. Along with the brain weight and head size, we also have a little bit of information about the gender and roughly the age category that the person fell into. But we're not going to really work with that so much. So in chapter 6, we learned how to interpret a histogram or a box and whisker plot to describe the distribution of a quantitative variable. So I have the distribution of brain weight and the distribution of head size here. What can you get from this as far as the relationship between them? We can't actually get any information about that because these variables are plotted separately, so we don't know which brain weight corresponds to which point for head size. The point here is that univariate, so that's one variable, summaries of bivariate, two variable data don't actually tell us anything about the relationship between the variables. To look at that relationship, we have to use a different type of plot. Alright, so if we plot for each individual data point, we plot the head size on the x-axis, the brain weight on the y-axis, and then just put a point representing the corresponding values for each individual observation. That gives us what is called a scatter plot. Hopefully this isn't the first time you've seen a scatter plot, but when we look at this chart, we can start to puzzle out what the relationship is between brain weight and head size. Right? There's a pretty significant clustering of these points along one particular direction. How would we go about describing that relationship between brain weight and head size? Well, we can use the direction, right? So is it sloping up or down? We can use the shape, so is it a line or a circle or whatever, and we can use the strength of the association between them. So if the points are only sort of kind of clustered around a line, then that's a fairly weak relationship. If the points exactly lie on a straight line, then that's an extremely strong relationship. Right? So let's look at each of these different ways to describe the relationship in turn. When we talk about the direction of a relationship, we're looking for some assessment of whether when x increases, y increases, or when x increases, y gets smaller. So if as x increases, y increases, we say that that's a positive relationship. We're going up the hill, right? If as x increases, y decreases, we say that's a negative relationship. So that would be, going down the hill. Right? So another way to describe the relationship between two variables would be to talk about the shape of the points. We've seen the linear relationship, right? Everything lies along an imaginary straight line. But there's other ways that points can be arranged. So the second plot shows a quadratic or curved relationship. You can kind of see the U shape there. The third plot shows a periodic relationship. This is pretty common to see with, say, like temperature data, where you have a fairly predictable increase and decrease in temperature over the course of like a week or a year. You'll often see this kind of periodic behavior. And the fourth plot, obviously, is a dinosaur-shaped relationship, and I'm not really sure what that means in science, but I really wanted an excuse to plot a dinosaur, so there you go. Alright, so we can also describe the relationship between two variables using the strength of an association. And so I've shown here 6 different plots moving from no association, so just a cluster of points, to very, very strong association, which everything lies very tightly along a line. When you have no association, my dad liked to describe this as if you shot a shotgun at the side of a barn, what the points would end up looking like. That's indicative of no association, right? It's just totally random point distribution. And as the strength increases, you can kind of start to see how there's maybe the barest hint of a line developing. And it's really not super visible until you get down to like the moderate strength relationship. But none of these particular descriptions, moderate or weak, there's no table of if it's this tight, then use this word. So you're just going to have to kind of call it like you see it, and as long as you're not saying that the bottom right plot has no association, you'll be fine. Right? So the strength of a linear relationship can also be described a little bit more precisely using something that's called the correlation coefficient. And I think this kind of thing arose out of a frustration with trying to describe the relationship using words like moderate or strong or very strong, and what does that exactly mean? So the correlation coefficient, which we use the letter R to represent that, lies between -1 and 1. So -1 is a perfect negative correlation, 0 is no correlation, and 1 is a perfect positive correlation. So you can see the R equals 0 looks more or less like that shotgun scatter that we talked about earlier. And R equals 0.2 still kind of looks like the shotgun scatter. R equals 0.4, you can start to see maybe some sort of linear trend there. R equals 0.6 is a much more coherent linear trend. R equals 0.8 is, again, even tighter. And then R equals 1 is a perfect line. Alright. Similarly, if we look at the negative side of the spectrum, you see more or less the same thing in reverse. You start with that perfect negative correlation, perfect straight line, and then the points branch out a little bit more each time until you're back at that shotgun scatter nothingness. I don't know if any of you guys like XKCD, but XKCD has a lot of regression-related comics, so this is not the only XKCD comic we're going to see today, but what Randall Munroe is saying in this one is that if you can't really figure out which direction the correlation is going, you might be better off just drawing some new constellations, because a very weak correlation is pretty hard to figure out what direction it's going. All right. So, with that said, I think it's probably worth taking a few minutes to get a sense of how the correlation coefficient works and what different R values end up looking like in practice. So I recommend that you pause the video at this point and go play the correlation guessing game for a few minutes. You can change the number of points and then generate a new sample and enter your correlation guess. I'm going to go with -0.8, and I was not that far off. You can even track your performance over time, which is kind of fun. So I recommend taking a few minutes and trying to get a sense for what different correlation values mean, and see if you can manage to get the errors to improve over time. Alright, so go ahead and pause the video for a bit. Now, assuming you're back, it's important to note that the correlation coefficient is only useful for showing the strength of a linear relationship. So if the relationship isn't linear, no matter what it actually is, the correlation coefficient is not going to help you. So all of these plots have the same mean, the same standard deviation for both x and y, and more or less the same correlation value of -0.6, 0.7, something like that. And you can see that some of them have a very clear association, right? If you've got a circle or a donut, there's a clear relationship between x and y. But the correlation coefficient doesn't actually reflect that. So just keep in mind that the correlation coefficient only describes linear relationships, right? So I'm not going to ever ask you to calculate this from scratch, not on an exam or anything else, but it might help to look at the equation and figure out how it's being calculated. So let's start out with the bit after the sum here. This is what that sigma means, is we want to add up all of the different data points from 1 to n, where n is the number of data points. We're going to take the x value, subtract the x mean, and divide by the standard deviation of x. And we're going to take that quantity and multiply it by the same thing done to the y coordinate. So if I have a x value that's a lot smaller than the mean, and a y value that is a lot smaller than the mean, I'm going to end up with a negative times a negative, which will be a fairly large positive value. So that's going to add quite a bit to my correlation and potentially contribute to a positive correlation, right? If I have a x value that is much smaller than the mean, and I have a y value that is much bigger than the y mean, then I'm going to have a large negative value. that is going to potentially contribute to having a negative correlation. Alright, so this dividing by the standard deviation just standardizes things so that everything can add up to at most 1. And we're taking the average here, so the average contribution over all of the data points. Don't worry about the n minus 1 specifically, but what you can see from this formula is that this is a measure of the actual association between x and y, and that, more importantly, that one big value, so a point that is really far out in x and y, will have an outsized influence on the correlation coefficient. Okay. So you may have heard before the phrase correlation is not causation, but it makes a pretty good chant, and it's really important to remind yourself every so often that just because two variables are associated and look like they're related, that doesn't mean that the x variable causes the y variable to change. And in social science, it's fairly common to kind of like flip a coin between which variable is going to be the explanatory and response variable. So even if we use one of them to explain the other, that doesn't mean that there is any sort of causal relationship there. Alright, so just a good little advertisement there for the fact that we need to keep things straight as to what we can and can't claim. Alright, so I mentioned that XKCD frequently weighs in on regression. So with one variable, it's pretty easy to spot the outlier, right? So here, this girl is the statistically significant other because he spends much more time with her than anyone else. It's pretty easy to spot an outlier in one variable. Right? It's just that point that's way out there. When there are two variables, you can have outliers in one variable or the other, but we also have to worry about things that aren't particularly excessive in x or y, but don't match the relationship with all the other points between x and y. Right? So here, you can see that if we have all of these black points, and we add in the red points, our correlation value changes a huge amount. Like it's less than half of what it was before. So these high influence points are, as you might guess from the name, having an outsized influence on the mathematical relationship between x and y that we're computing here. Alright, so the book's definition of a high influence point is a point that will change what we think the relationship between x and y might be. Alright, so you'll notice that the red points in this particular animation aren't excessive in either x or y. That there are other points that have x values that are about that extreme. There are other points that have y values that are about that extreme. What makes them exceptional is the fact that the x and y values don't match the relationship with the other points. Okay. Now, just another example of this phenomenon is that if we have some points that are out at the end of x and have exceptional y values, we can actually find ourselves with something that looks like a linear relationship that's mostly just due to the outliers. So as soon as the outliers are added, the correlation coefficient jumps quite a bit, almost doubles, and before that, these points were pretty much, there was no relationship between x and y. So when you're describing the relationship between two sets of points, it's important to talk about the outliers or high influence points as well. Um, so, but only if they're there, and there's no guarantee that you're ever going to have high influence points. A lot of times you don't end up having that. All right. So with that, I'm going to recommend that you work through Exploration 10.1. That'll give you the chance to kind of think through this material in practice. I have added it as an assignment on Canvas. You do not have to upload Exploration 10.1 unless you want to, but if you do it, you can get 10 points of extra credit on your assignments category to make up for any assignments that you might have missed in the past. Alright? So, as always, please feel free to set up an appointment with me using the Calendly link that's in the announcements page. Send me an email, post on the discussion boards if you have a question or there's something that you can't figure out. And as a reminder, I'm giving bonus points for participating in the discussion boards as well, so please keep that in mind if you are getting towards the end of the semester and worrying about your grade. Alright? Thanks a lot. Hope you guys are safe and well and not going stir crazy.